Good evening, everyone, and welcome to today's topic of Saturday Talk by JanyuTechnologies. Today we have Professor P.B. Sujit ji for today's session. A brief introduction of Sujit ji. Mr. P.B. Sujit is a professor in the Department of Electrical Engineering and Computer Science at IISER Bhopal since year 2019. Before that, he worked at the IIT Delhi, University of Porto, and BYU. He received his PhD IISc, and his research interests are in multi-robot systems, guidance and control of unmanned vehicles, and human-swarm interaction. He is already associated with JanyuTechnologies, and we are jointly working on a couple of projects in the field of swarm technology. He has also shared a technical abstract of today's speech. I'll request Sujit sir himself to explain it to the audience. And today he is going to speak on the topic that is off-road autonomy for unmanned ground vehicles. Over to you, Professor Sujit, from here. Thank you so much.
Thanks, Rajesh. And also thanks to Bhushan for reaching out. And it's a great opportunity to talk to all you guys. So what I'll do is that I'll just give a brief intro of several works that I work and then go into the talk on the off-road autonomy. So the outline is going to be, initially I'll just discuss about on-road and off-road, why there is a difference between these two, give some background on the challenges as well as different data sets that are available for both of them. And then we'll move into the off-road side, wherein we'll talk about first the segmentation framework, which is OffSeg, then a cost map generation by learning on the entire cost map itself so that the human bias is removed, and then with any traverse framework wherein we want to put a human operator in the loop while generating these navigable regions, and then some conclusions. So here we work on several things, from let's say doing some landing to a little bit on road as well, wherein we want to develop different architectures such that they are much easier to use and they can be deployable on the robots. So apart from this, since there is a interest in the multi-robot systems as well as on different types of vehicles, so here we have worked on this is a deep reinforcement learning based cooperative strategy, wherein we want to develop algorithms such that you are always in some kind of a communication framework with respect to other agents, so that you can do both the localization with respect to another agent in terms of ranging and bearing angles, while in other case you want to use this in relay systems, stuff like that, wherein you want to make sure that the agents are able to cover the region as well as have the connectivity constraints that are associated with it, which could be data constraints with the transmission constraints, or it could be a localization constraints, whichever way you want to pose the problem around. And the other is we worked on different bathymetry applications, wherein we want to generate lake beds rapid rate, because they are pretty expensive in terms of deployment and the manpower used and the kind of sensors that are used. So depending on the lake size, the amount of people that needs to be deployed to get everything working, transportation, all these costs just add up. So what we want to do was that we want to come up with a very low cost solution, wherein you can take the surface board with you and then just deploy it given the map that you want to map it up in terms of coordinates, and then use adaptive sampling such that you sample those regions where the information is high, such that your uncertainty reduces significantly, while trying to achieve a similar kind of a performance to that of an bathymetry, wherein you do a up and down swathing kind of a system that is typically done here, right? So here, for instance, this is in a simulated field, but let's say that we have an proposed approach. Here you can see that the error distance traveled is so less, while we can reduce the mapping error to a very significant extent compared to any kind of an existing there. So you can get close to, let's say, 60 to 70% reduced distance compared to the lawnmower way. Yeah. So these are some different aspects that we have done. This is another one wherein we want to do a cooperative encircling of the rover. This is for a single agent, and then I think this is followed by a multiple agents wherein we want to continuously, persistently track this target. Yeah, I hope it runs. Yeah. So these are small. It's the experiments are done in the lab, but the same kind of an algorithm that can be deployed on the outdoor as well. Yeah. So with this, so what we'll do is that we'll try to go into the main topic, which is the autonomy for off-road vehicles. So one of the first things is why off-road. So in case of an on-road autonomy is where you want to have your cars driving with ADAS 5, ADAS 6, something like that, so that the vehicle can autonomously track the lanes, avoid obstacles, follow traffic signals, all these aspects, right? So there are many companies that are already working, like say Waymo, Tesla, or now Cruise. So why they are able to do, or a lot of academic research can be done in this area of on road, because there are several data sets that are available, which is very much essential, considering that most of them use some kind of a deep learning aspect, right? So for instance, there are data sets on cityscapes. You have a kitty data set on which tens of papers have comes out, and then you have too simple, or there are more than 50 plus high quality data sets that are available. And top of this, you also have simulators like say Carla, AirSim, but then I think now AirSim has been rechanged to something like Colosseum, it is called. And similar to that, you have others based on different OD dynamics, right? You have a car sim, you have torso, like different simulators are available for you to use. On the other hand, if I take it for an off-road, wherein we are interested in doing any kind of an autonomy in the off-road segment, so we know that there are plenty of applications. So these are not on the road, but you have, like, say, for instance, simple thing could be when your agriculture is an off-road environment, right? Wherein you want to automate the way in which the plowing or the seeding or the fertilizer, pesticides, all these are coming into it. The other is on different military applications along the borders you have, and several disaster management requirements, especially when there is some kind of a flood or any kind of an earthquake or any kind of a natural disaster that happens. It's not that it is limited to only on road. So when you just move away from the main road, then it more or less like you are into trouble, that most of the ones that have been trained on this kind of data sets where we have a predefined road comes into picture is no more useful. So how is our off-road different from on-road environments? These are unstructured boundaries, don't have any kind of an restriction saying that you need to be in this lane or you need to be in a road where it is only the tar road or the cement road is there. You have uneven terrains, you have both negative obstacles that can go down, as well as you have small rocks, you have a little bit of high mud mounds and things like that, right? So terrain is no more even on which you want to do a path. So, and then most of the data sets that are there will have unbalanced class distribution. So what does this mean? So when we do any kind of an training using deep learning for even let's say that you want to find the lane of a road, right? You collect a lot of data and then you label the data such that you're telling what is a lane class and then everything else is non-lane class, let's say. But what happens here is that in terms of off-road, in one patch of the area you will have certain things, let's say the log or any kind of a potholes or anything like that, right? Puddles, things like that. But the rest of the entire data set you will never come across. You'll just come across only for few frames or even maybe a single frame, right? So if you take the thousands of images and the amount of time that the same kind of a data that is available is very less, then you end up getting an unbalanced class distribution, because let's say that it is a puddle, then the amount of images that have puddle are, let's say 10, while you have 10,000 images, let's say. So there is a big class distribution imbalance in terms of class distribution that will cause your models to fail whenever if there is any kind of a small variation, or even ability to detect reduces significantly because it has not been able to see sufficient number of times. So that is one of the biggest issue in terms of data sets. And also the number of data sets that are really available open source and with good annotation is very few. You have rugged data set in Europe, and then you have Release 3D. This is from Shrikant in Texas A&M, and then you have a Deep Scene. I think this is coming from Freiburg University again from Europe side. So, but these are very few, and then maybe one or two more over time they have not come. But the number of data sets that are very few compared to tens of data sets that are available for the on-road driving side. Right? Apart from that, different environments, right? So require different kinds of setting, right? So what you see here is, although it is an RC-based control, it is trying to move or trying to travel through the sand pitch, or you want to recognize that this is a sinking sand, so you should not be traveling. Well, on the other hand, if the water density was not high enough, then you could have easily crossed it through, right? So you need to understand the scene. You need to get a better understanding what is traversable and what is non-traversable in these kind of other is, although we will not be touching on this, the other is going to be on the dynamics and stability of the vehicle. You need to take that into consideration when you want to say whether some regions are not traversable or non-traversable. Here, although we are not going to generate any kind of a controllers for this, but let's say that you already have existing ones, then how can we better use it such that you give them reasonable parts such that the vehicle can handle, rather than giving something that the vehicle cannot handle and saying that no, you have to do this just because it's of need, right? So these are some inherent problems as well as challenges in terms of off-road autonomy that actually requires a lot of attention as well as patience in dealing with these off-road environments, simply because the environments are now very much representative to the particular areas, right? It's not so generic, but at the same time we need all sorts of autonomy for these kind of vehicles. So considering these different problems, so what we thought was that it is very essential for us to really understand at the bottom, like how can we generate navigable regions in the first plot, right? First part of the solution, because what is navigable for a particular kind of a vehicle may not be possible for another kind of vehicle. Can we take that into account, or is it like, okay, given a data set, you just want to look at find what is a navigable region for this particular data set. So what we did was that we tried to understand that by looking at now what is the characteristics of each of these data sets. If you take Release 3D, so this is an off-road environment in the Release campus at Texas A&M. It has 13,000 approximately LiDAR scenes that are annotated, 6,000 odd images that are annotated. Along with it has a GPS and IMU data, which you can use it for training any kind of a model that we want. So it presents challenges to existing related because of the class imbalance. Some of the classes are very, very few, and others are plenty of them. Okay, and it provides benchmark for image and cloud point segmentation algorithms for off-road. So these are the different classes that we can see in this particular data set. So they have approximately, I think it is 18 classes or something like that. 18 or 20 of them. So on the 19 of the 19 data classes are there. So you can see that in the end, like you have sky, grass, tree, bush. These seems to having very high number of classes, while other hand, person, puddle, rubble, asphalt, water, building, they have very, very low. So there is a very significant class imbalance that happens, because of which really when the release paper came, so they tried on two existing state-of-the-art segmentation frameworks. One was BiceNest and HRNet, and the accuracies were around 30 to 40%. The other one is a rugged data set that has a 24 semantic categories, and then they have approximately 7,500 annotated images, which we can use it for doing the classification stuff. Other is called DeepSyn, so that has RGB, depth, NIR, NRG, NDVI, EVI, and their variants. You can get a very good, nice, different images, but the entire thing was traversed for about 4.7 kilometers each day, and then they did it for several days, I think approximately a week or 10 days or something like that. So they have pretty good amount of data, but it is very well, it's not really that off-road in the sense that wherein you have logs or it is traveling over the logs into the forest or anything like that. So, but it has a pretty good, decent off-road environment. So manually annotated pixel-wise ground truths that are available, which can be used. So what we want to do is that we want to remove that. So we want to learn actually the cost map itself. We used the same camera images. We assume we have a camera as well as a LiDAR. Right? From this camera images, we get the off-road, we get the offset images, and then we have a point cloud. We fuse these two as my input data to a neural network, so which is my camel framework, which I call it as. And then I use it to a navigation stack that will determine what should be the path and what is the next steering commands that I should be taking. So given the current heading and the desired heading, the errors that will go in as an input back to the environment, which in turn gets the input data to the camera. So this is the entire framework which the complete system works with. And it eliminates the human bias with respect to the cost map generation. So one way of looking at it is that if I just use these images and then do an average slope, and then you can see that most of the places it is flat, while others it has a lot of different values. Similarly, you have it for height, you have a LiDAR intensity, and then you have LiDAR semantics that are coming up. So what we did, so we used a multi-scale fully convolutional network inside, so that it can learn the way in which the map, the steering command can be generated, and the cost map is also generated. So one of the things is that because now we have only a data, but rather given the kind of command, the vehicle reacts in a differently. So we need some kind of a simulator to do this, for which we use the maps. So other thing is that for determining where the direction should go, we just use a simple star to give us the raw path. So this is the navigation stack, the generated path, and then you have the steering. So initially, for us to learn different cost maps, so we just run the vehicle in an RC control mode or in a joystick, or using just the arrow keys in the map simulator, and then try to collect different data. Okay? So as the vehicle is moving, you will see that because the human operator is telling which direction you should move, and then operator typically tells in the direction where there are no obstacles around. So we generate those kind of paths, right? So those becomes like your reference path, which the navigation stack is going to understand, and then we create the artificial goal points for each and every frame, and then generate a star, so that will tell me the path, and then have my desired steering angle that is going to give me the error such that I want to steer my vehicle towards that. So this is the kind of the images that you get. Top 3 are your camera images. The D is your LiDAR point, which has been flattened down. So this gives you the complete, you can see a lot of trees and then free space that is there. And then the corresponding embedded images for these inputs. Then we did a training which was decent enough for us to say that now we can go in and then do some kind of a evaluation. So this is on the map simulator. We have this was done on i9 with a 360 RTX GPU, okay? And then we had a decent inference speed with approximately 92 milliseconds for each image. So you have 3 cameras, 3 images are coming in, and then you have the projected point that coming in. And then after that you get the cost map on which we just use the A-star to generate these paths. And then these parts is given to the steering controller to generate the steering angle. So a difference between how a manually evaluated and then learn cost map for a particular scene is shown here. Where your green is your handcrafted cost map, right? A generated shortcut, but it passes close to the trees. And then red is the one that has been generated by the camel, and then blue is generated from closely designed cost map. So giving different values can generate you different paths. So these are different, tested on different terrains. So here there is no end goal. Okay, so it's not like here we are just only finding out regions where you have a free space to go, and then it is just exploring without any end navigation or directed goal navigation is not embedded into this particular work. So here we are more concerned about, okay, how do you generate the cost map considering that you want to eliminate the presence of human bias into it. So then we did an experiment in the campus. So this is the right camera, left camera. We used while training, we trained with the 3 cameras because it's easy to use how many ever we want in the simulator. But in the real world test, we used only 2 cameras. And then this is the projected LiDAR. We used LiDAR VLP16. And then we had an AGX Xavier on board to determine the navigable, to determine the cost map, and then generate the artificial goal through which the path planner is moving on. So we did it for what's close to 400 meters from here to somewhere around here. From here to here we did close to 400 meters, and it worked reasonably well. So system biases and sensors, because we did not calibrate any of them, but still it worked well. And training, we had multiple, 3 sensors, while on the testing we just used only 2, but still it was able to perform well. But everything doesn't go, as you know, you have also been in the field. Like for instance, in the initial phases, it could wrongly classify stuff and then go into different places. And then sometimes it also used to get stuck. But these are things like we learn on the fly, like what are the different in terms of optimization with respect to your code. Sometimes it gets stuck, and then samples it takes, but your ROS node is just publishing it off, and so the vehicle is steering away, right? So these are some of the things that you forget in the field. So this is about the camel framework. So the other one is about the AnyTraverse. So after doing this, then we realized that the kind of environments that we tend to work, let's say even in the field when we're doing between different seasons, what is navigable in the summer season was not navigable in the rainy season at all. So other thing is that so if I'm using a let's say tractor kind of a vehicle, then I can have almost many things as navigable, right? But on the other hand, if I have a small robot, the one that we had, then because of the low clearance, I can't say everything is navigable. So we want to understand more about what is navigable and non-navigable regions, but at the same time, how can we adapt to different environments? Because having a single model that typically model doesn't have the vehicle dynamics or the kind of vehicle that we use as an input at all, right? So we only have the images that are popping in, or the sensors that can be popped in, but not on the vehicle side of it. So what we thought was that let's see how we actually as a humans try to navigate in these environments. When we go very first time, we just don't go alone, right? We go with some people around, right? Or we go with an expert. And anytime we want to navigate or we want to travel, we just something that we don't know, we just ask to the expert, like, is this road or this way, can we walk along this way or not, right? So we want to get in that human operator aspect into the picture. So, and in order to have this conversation or discussion, we thought that it is a good way for us to use vision language models that can give both the text as well as the segmentation part for us wherever we have any kind of an issue, so that the human operator can help us. So this has appeared in the IISER 2025. So the key concept here is 2 things. One is to use vision language models that help us in understanding both the segmentation as well as operator inputs taking in the human in the loop aspect. much easier. And how does the VLMs really help, or are they really effective, or is it just the hype that comes with VLMs that we just want to navigate around? We try to look at it. One way is that very large set of features. Is VLM effective? No fixed classes, works with natural languages on images. We don't need to tell that we need 24 classes on which we are working, or 20 classes on which we are working, or 4 classes, because it has been trained on such a very large data set that you hope that for most of the cases you tend to have some kind of at least initial feature extraction that pops up. If high variance for some type of features in the different environments that we come across, test embedding module captures semantic meaning rather than fixed learn features, which can use it. And then enormous data requirement for adaptation. If you use a VLM, because it has already been trained on such a large data set, you don't need that much. You can actually do it with just existing VLM, but then the way in which you give the prompts can be properly integrated to try to see what can come over. So for the human in the loop operator, so given a natural language prompt, some input, VLM can point out which area in the image its segments. Let's say that we want to do some kind of a navigable region, but rather than just telling give me a navigable region, but rather we can just start with, okay, give me the regions that are having green grass. Right? So that it gives you all the parts of the segment with the green grasses. So then on top of that, now you can ask whether, now given the fact that it is a green grass that is available, if it is a very small patch, is it navigable or non-navigable, right? For different kinds of vehicles. The given environment plus the robot, what should be the prompt? Which prompt is for traversable and which is for non-traversable? And then we need to use human expertise in deciding whether it's a traversable or a non-traversable prompt. The other thing is that you don't want human operated for each and every time again and again. Right? You want also to reduce the overload on the couple of things that we kept in mind while designing this methodology. So one way of looking at it, this is the scene. This is in one of the, I think it's a forest-based small park near Bhopal. So if this is the scene, and then I have 2 different robots that want to go. One way is that I can tell to the quadruped, let's say that I will give weight as the grass and then rock, because it's a small rocks, they can easily navigate. However, bushes it can't navigate. Why it can't navigate? Because the way in which the quadruped is made to change its the legs is that it tries to drag closer to the ground. Because it is trying to drag closer to the ground, there's bushes, right? So this, especially those grass, they get entangled under the leg and it will just fall down. It won't be able to move around. This is something that we did it in the campus, and then we realized that this is the issue over here, and hence we should put a bush or something that is not navigable at all. On the other hand, if it is like a robot that we saw in the earlier cases, it has a very low clearance, which means that this kind of a small rocks can also be a problem. So where rock becomes a non-traversable, while bush and the grass can become a traversable for this. So depending on the context, like we just asked to the operator how we can use it. So that was the entire framework on which we are. So the AnyTravers, you have 2 things: traversable segmentation, which pixels are traversable, human traversable. Should I ask the human for help or not? So for this we use 2 things. One, we use the scene history, and we use a memory, so that once the operator says that this particular object that you're looking at is a traversable, then you keep that in the memory so that you don't need to ask the operator again and again whenever you see. For instance, you saw a dirt on the road, right? And then the operator says that you can navigate on the road. So then next time you say it, you should not ask that is it navigable or not, which is something that you want to keep it inside your memory so that you can continuously process.